for those who are out. Welcome, welcome, welcome. I'm Lisa Blackburn. This is my YouTube channel where we talk about everything I want to, science and math. Today we are doing the notes for Unit 8, Heat, and it's going to be very exciting as soon as I find my pen. Here it is. All right, so which has more heat? A teacup of boiling water or Lake Allatoona at 60 degrees Fahrenheit? What do you think? You would think a teacup because it has a higher temperature, but it's the lake. Because it's heat is all the energy in something. It's all that energy that's in the chemical bonds. And imagine if we broke all the chemical bonds in Lake Allatoona. I think we might blow up Atlanta. So it would be a lot of energy stored there. The teacup doesn't have enough bonds that even though it's hotter. So the takeaway is there is a difference between temperature and heat. Heat, let me get my notes and make sure I write down the same words I put before, because there's more than one thing that you can put in these blanks. Yep, that's what I thought it was. Heat is the total amount of energy that can be transferred. Now, how is energy transferred, do you think? From low to high or high to low? High to low. High to low. And so like heat always goes from something hotter to something that's colder. And temperature, heat can be measured in joules, spelled different than like diamonds and rubies, or it can be measured in calories. Did y'all remember to do your food diary for 3 days? If not, you can start today, because we're not actually going to do the lab with that till Thursday. So write down everything you ate today, everything you eat tomorrow, everything you eat Tuesday, and you'll have your data for your lab that we're going to do on Thursday. Test Friday. So don't forget, write it down. Just writing it down is going to be worth 1 grade, because I know it's a pain. So it's going to be worth double. Yes, William? Yes, you should. You should. Everybody should do that. All right. So temperature is different than heat. Temperature is the average kinetic energy. The average kinetic energy, and it's measured in Celsius or Kelvin in science. What's it measured in English? It's what you're more used to. Fahrenheit. Or Fahrenheit. Now, so let's talk about temperature for a second. So right now, my water bottle on the table looks like it's perfectly still. But if you could get in a little, shrinker from Honey, I Shrunk the Kids and go in it all the way down to the atomic level, or like Ant-Man, remember how he went into the quantum world? You would see the atoms vibrating. They vibrate. They have kinetic energy all the way down into absolute zero, which is the point where all molecular motion ceases. Now, it's sort of theoretical because we haven't actually reached it, but we think all molecular motion would cease. The reason why we haven't reached it is to cool something down, you have to have something colder than that to get it down to that temperature, and you can't have anything colder than absolute zero. So, but they try, and when they get down close to it, weird things happen. The rules of physics seem to be different. So that's another area of science that's still wide open for you to learn more about. So another thing is phase change. What is phase change? Yes, going from a liquid to a solid to a gas. And it takes energy to do that. So this is one of our standards over here, right here. It says that you need to understand this graph. So this graph is going to be on the test. Can I roll up? Are we good? Do I need to roll back? You want to go back up a little bit? I'll leave it right there, because then you can still see it. So this is our graph. This is a phase change graph, and what it means is, as you add energy, things go from solid to liquid to gas, just like how Nevaeh said. But in between, when it's at the point of melting or when it's at the point of boiling, if you add energy, the temperature does not go up. See how they're flat right here? So that means all ice water is 32 degrees Fahrenheit, 0 degrees Celsius. It doesn't matter if you chill it down or heat it up a little bit, it will stay at 0 until every single chemical bond of the lattice is broken and the molecules are free to move around. And then if you heat it up, it'll heat up some more, all the way to boiling. Once it gets to boiling, it's going to stay at 100 degrees Celsius, 212 Fahrenheit, until every bit of that water has boiled away and become steam. Then it will heat up some more. So even if you add more, fire to it or heat, it doesn't heat up. It will stay at the temperature there. Does that make sense to you? All the energy is being used to overcome phase change. And it won't heat up until that happens. Yes? Are we going to have to know what? Still can't hear you. You got to yell at me. Yes. So I'm going to get about 10 test questions right here. So you're going to be matching these and including what I'm going to show you in the next part when I get to scroll. Okay. So there's two kinds of heat here. So first of all, temperature does not change. It does not change while phase change is happening. And that is, when you add heat to it and it doesn't increase in temperature, that's called latent heat. So draw a little line that this is where latent heat is. And then I'm going to change colors. I think that'll make it better. If you add heat and the temperature does go up, that's called sensible heat. And that's in these places. That's the sensible heat. So you see where I can get a lot of questions from that graph, can't I? Where is it latent? Where is it sensible? Wyatt, put your phone away. Pay attention. Sensible heat, latent heat. All right, let's go on. Can I move it now? Yes? All right. Now, you already know this next part. We're just reviewing it. What is a reaction called when it gets cold and energy goes in? Endothermic, yes. And what is it called when it gets hot and energy goes out of the reaction? Exothermic. And we see that therm means heat. Okay, exo, it's exiting, endo, it's going endo. Now you need to memorize this also. For water, what temperature does water melt at? What temperature does ice melt or water freeze? It's the same temperature. And what is it in Celsius? 0. So it's 0 degrees Celsius or 32 degrees Fahrenheit. What temperature does it boil at? 100 degrees Celsius, and what is it in Fahrenheit? 212, very good. And I want you to know both of these, even the English part, because it's part of you just knowing stuff. Now, what is subliming besides a donut place down near Georgia Tech in Atlanta? And I don't think they're very good, despite the article I read on them. Don't tell them. Shh. Has anybody else had the Sublime Donuts by Georgia Tech? Not all that good. What is subliming, Jay? Close. Not liquid to gas. Solid to gas. Solid to gas, yes. And so, have you ever seen dry ice? It just goes straight from ice to smoke. It does not melt. So that's subliming. Subliming, the temperature for water depends. It depends on how dry the air is. It depends on pressure. So it depends. But I want you to know what subliming is. And it's not at a certain temperature. May I scroll? Let's see, yes. All right, find the button. Button, where's the button? There's the button. Whoop. Okay, so there is another thing that you have to learn the definition of. It is called specific heat. Specific heat. It is a physical property of a substance. You look it up in tables. And this is the definition. It's the amount of energy needed to change the temperature of 1 gram of substance 1 degree Celsius. Okay? Now, the symbol for it is C. It must have lost in the wars of who gets the symbol after their name. And you already know about this a little bit, okay? But let's see if y'all can figure this out. If I have two pans, and I am going to cook something, so I have an aluminum pan on the stove and a pan of water, but then my friend calls and says, let's go to the movies, let's go see Black Widow. And I'm like, okay, let's go. My friend Helen would be the one who'd want to go. So I turn them off, and then right before I leave, I come back to check and see if they're off, and one of them has cooled down and the other one is still hot. Which one cools off first, the water or the aluminum? The aluminum. Y'all are the first class to figure that out. It's the aluminum. The reason why is aluminum has a low specific heat, and water has a high specific heat. Water has a high specific heat. Aluminum has a low specific heat. It means it takes a long time for water to heat up. But once it's heated up, it holds that heat a long time. Aluminum heats up very quickly, but it also cools off very quickly. It makes sense? The reason why is water is shaped like Mickey Mouse, M-I-C-K-E-Y-M-O-U-S-E, and is polar. Remember, we already learned about that in our bonding chapter about how things can have a positive and negative end, and because of that, sticks to itself. So this is where you might have noticed it. You go to unload the dishwasher. This might be your chore at your house. It just quit. And you don't go and grab the glasses first, do you? They're too hot. First, you grab the wooden spoons. They're going to have the lowest specific heat. Then you're going to go for the aluminum baking sheet, the silverware, it's not too hot. Next, you go for the ceramic. But the very last thing, the thing with the highest specific heat, is that glass. It's going to take the longest for it to cool off, right? You see, you know about specific heat. You just didn't know what to call it. Okay, the fancy science word for heat is enthalpy, and it makes sense because we're used to TH, the, meaning heat. Thermal underwear, thermic. So you're used to therm being heat, right? That makes sense. And there's more to enthalpy than heat, but that's a good way to just think of it for now. And there's a formula that you can use that's our one big math formula for this unit that is how you can calculate heat. Now, sometimes it's H for heat, sometimes it's capital Q for heat, and sometimes it's lowercase q for heat. They're all the same thing, and you need to know it. You need to know they're all heat. Now, here's the formula. Heat equals mass times specific heat times change in temperature. But you can remember it because it looks like it says heat equals cat. So there's our cat. Do you see how it looks like it's saying cat? Heat equals cat. So M stands for mass in grams. C is specific heat. T is temperature in Celsius. And what does a triangle stand for in science? Change or difference. What do you do in math for difference? Add, subtract, multiply, or divide? You subtract, right? Yeah. So we're going to be given two temperatures and we're going to subtract and find delta T. How do you feel about that? Not hard? Not a bad one? I have already sent you a message in Canvas with the answers to the worksheet. So you can try a problem, check it. Try a problem, check it. And there may or may not be a pop quiz tomorrow on this hint. So do your homework. All right, so here's our example problem. You drink 1,000 grams of ice water. When you do this, annotate it. That's a mass. At 0 degrees Celsius, that's the temperature. It warms up to 37 degrees Celsius. There's our other temperature. There'll always be two because we have to subtract. What is the change of heat? So what we're looking for is heat. That's our formula. We substitute it in, multiply, and what did you get? I got 154,000 600 joules. Now, how do we measure this? We're going to do this in our lab tomorrow. It's with a device called a calorimeter. It looks like it's calorie meter. And you can see what real ones that they use in industry look like when they're figuring out how many calories are in your sour gummy worm that you might be eating. But we are not going to use a fancy one. We're going to use this third one. Can you read the real little writing that says what it is? It's a styrofoam cup from Walmart. Great value brand. So we're going to do a lab tomorrow with this, where we are going to figure out the heat, the change in heat. Okay, what about units? Heat can be measured in joules or calories. You're familiar with calories with food. That's why you're doing your food diary. And we're going to do a lab on that. A calorie is 1.84 joules, so that's our conversion factor. Sometimes you need that in these problems. Now, food calories and physics or chemistry calories are different. They don't want to scare you off from eating food, because one food calorie is 1,000 physics calorie. So if on your Snickers bar it says it's 240 calories, it's really 240,000 calories. See, that might make you think, oh, maybe I shouldn't eat that. So the food industry has decided to put kilocalories on there instead. Now, entropy. Entropy, delta S, is another thing that drives reactions. Heat and entropy drive reactions. So what is entropy? It also lost in the battle of symbols. It's delta S. It is a measure of the degree of disorder in a system. It is a law like gravity. Remember, laws beat theories. It always goes from let me see which way I wrote this. See what my blanks are. That's what I said. From more order to less order unless acted upon by an outside force. That's the law of entropy. So for example, your room. It is a mess. Will it clean itself unless you're Mary Poppins and using magic? Can your room clean itself? Wyatt, wake up. Do you have the answer there, Sebastian? Can your room clean itself? No, it cannot. So your room will goes naturally to less order. It takes you, the outside force, to clean it up. So it takes an outside force. Another thing is I have drawn in your paper a covered wagon. Do you see that? That's because at Six Flags, when I was a girl back in the 70s, Six Flags was a little better at keeping up. And the Dahlonega Mine Train, have y'all ridden that? It was themed for the gold rush in Dahlonega that was before the gold rush in California. And they used to have a covered wagon sitting near that part that goes in a circle. And it had a cover on it, and it was a little covered wagon, had little barrels in it to be like the gunpowder to make the mine. Well, over the years, I've seen that thing fall apart. First, the cover was gone, ripped off. Then the wood started rotting, and the wheels fell off of it, and it was just sitting on the ground. Then the wood rotted completely, and if you go to Six Flags now, it is still there, and it's just some rusty bits laying there next to that part of the roller coaster. But no one did that to it. It naturally went from more order, those molecules in the covered wagon, to less order, what they are now, because it was not acted upon by an outside force. Now, Disney would have acted upon it, and they would have kept that looking good, but not Six Flags. I love Six Flags, but they are not the same as Disney, are they? No. All right, so this is a little bit of a problem scientifically. Why? What two theories do we have that violate this law of entropy? What two theories do we have where things are going from disorder to order without being acted upon by an outside force?
Big Bang Theory?
And?
I don't know the other one.
Evolution. Both of those. Big Bang, remember, we're starting with a baseball size of matter. It explodes, and we get out of it all of our galaxies and planets and stars. It's an explosion where out of that explosion came order. it violates the law of entropy. So do we know everything about this? No. Stuff for you to learn, right? For you to discover. Also evolution. Evolution, start, primordial muck, biomolecules assembling into single-celled organisms. You're not a single-celled organism. You're fancy. You're multicellular. You are extremely complex. Moving from simplicity, single-celled organism, to complex, you, without being acted upon by an outside force. Do you see the problem? Do we know everything about this? No, we do not. There are still mysteries in the universe that we need to figure out. All right, but this is what we do know. We know about right now. We don't know about the past, but we know about right now. Enthalpy, heat, and entropy, order, are the things that drive reactions. They drive reactions. Now, there was a guy named Hess. He's in our standard over here. Hess's law. And he figured out that these energy changes are the same whether the chemical reaction takes place in one step or in several steps. It's like if you're making a cake and you make the cake all at once or you make it over days. First you make your cake, then you chill it so you can get the icing on real good. That's what the professional bakers do, you know. It doesn't matter. In the end, it takes the same amount of energy whether you do it at once or in steps. Another implication of Hess's law is that if a reaction is reversed, the sign of the change in heat is also reversed. So if you have some reaction that is reversible, then you can change the signs of these. And so a lot of times you have to change the sign in the math. So this is sort of just saying, hey, guess what? You're allowed to change the signs on these things if you need to. We're going to do a fancy little math problem where we are going to set two different delta H's formulas against each other, and one will be positive and one will be negative, because the heat gained by one thing is lost by the other. That's another implication to the math. Okay, so here's an example problem. Diamond and graphite. Graphite in your pencil, diamond might be on your ring. Okay? These are allotropes. That's science fancy word for two different forms of the same element. Carbon can be a diamond. Carbon can be graphite. It can also be buckyballs and bucky tubes. So now they've discovered some new allotropes of sulfur. So this should say same. The same chemical carbon, and we're going to talk about it being in two forms. Okay? You can burn a diamond and turn it into graphite. Remember when we saw Julia Child do that in our video? And he burnt green beans and they both turned into carbon. But you can also reverse this reaction. You can add energy to graphite and make a diamond. Now, is it a good diamond? No. Is it jewel quality? No. But can you make a diamond? Yes. Turns out you can. Now, how much energy does it take? The enthalpies for graphite is this and diamond is that. How you do the math is you add them together, but you change the sign of one. Remember, what do two negatives make in math? A positive. And so you end up with the difference between these two, and it takes 2 kilojoules of energy. If you want to make a diamond, that's what it's going to take. Now, last little idea here. Where'd my button go? There it went. Whoop. More fun with sound effects. Thermodynamics. Okay, I have told you over and over again the law of conservation of mass and energy. Matter and energy are neither created or destroyed. They just change from one form to another since creation, right? Okay. Well, if you look at just the energy part of it, it's called thermodynamics. It's the law of conservation of energy. Just the energy part. It's also called the first law of thermodynamics. The second law of thermodynamics is the law of entropy, that things move from order to disorder unless acted upon by an outside force. Okay, getting these in your head? So another way to say this is the energy of the universe is constant. We're not gaining energy, we're not losing energy. The energy of the universe is constant. Ta-da! Not too bad. You're going to be ready for a test on this by Friday, right? One math problem, bit of vocabulary, a graph, easy peasy. All right, I'm going to stop the video. Science is great.